Hello everyone and welcome to the channel. In this video, I'm going to debate with Data and Facts if it's still worth learning about internal combustion engines. This question is relevant today, especially because of the big push from governments all over the world for electrification, especially in the passenger vehicle industry. Stay tuned for all the details. Now let's discuss which industries are using internal combustion engines. First of all, we have automotive. This is a well-known industry because everybody either has a car or is using a car as mode of transportation. So everything from passenger cars, motorcycles, trucks, and buses are using internal combustion engines, and most of the powertrain currently are having internal combustion engines as a prime mover. Then we have aerospace or aviation, and still we have a lot of small airplanes and helicopters which do have internal combustion engines as a prime mover. Then marine, we have cargo ships, fishing boats, ferries, and personal yacht powered by internal combustion engines. For cargo ships especially, internal combustion engines, I think currently are the only way to go because they are traveling very long distances, hundreds, thousands of kilometers, and they need to have enough fuel to, for example, cross the Atlantic Ocean. There is no refueling station in the Atlantic, and then it's very important that the energy density of the fuel is high enough so it's going to power the cargo ship from one coast to the other. Then we have agriculture, where we have tractors, harvesters, and crop sprayers. Again, these are machines which are under a lot of load. They have to work into extreme conditions, and in a remote field, you don't have other means of energy, which means that your fuel should be enough to perform the duties you have. Next, we move to construction and mining. So all the excavators, bulldozers, dump trucks, and loaders, all of them are powered by internal combustion engines. And then we have power generation. So we have stationary generators and portable generation sets. These are especially important in remote areas where there is no connection to the grid. These are also used as backup power stations. So in case of the grid goes down for whatever reason, then you have this kind of generators which are providing power. And then you have railway. There are still in use a lot of diesel electric locomotives. These are basically series hybrids where the diesel engine is run as a generator. So basically the diesel engine is connected to an electrical generator, produces current, and that current is powering a electric traction motors which moves the locomotive. But the main power comes from the diesel engine, and again, where you have railway going through remote areas, deserts, forests, and so on, when there is no electrified lines, diesel electric is the only way to go. And last but not least, we have forestry equipment with chainsaws, log skidders, and wood chippers. These are powered also by internal combustion engines. So as you can see, most of the industries which require movement, all of them have more or less, probably more, internal combustion as prime movers, right? In the media and also what you see, online, everybody focuses on the automotive domain, but that's only a small chunk of all the industries which are powered by internal combustion engines. So, from the application point of view, only if you look at the number of industries using internal combustion engine, it's still worth learning about how they operate, how to design, and how to repair and maintain. Now let's have a look into how an internal combustion engine has evolved during time. So if you look at this example, where we have a Benz patented motor wagon engine, it was patented in 1886. So as you can see from the image, it's a very simple setup. It's a single cylinder, single piston engine. It's air cooled. It's atmospheric, has atmospheric intake, and there are no sensors or electronics. So everything is mechanical or pneumatic. Yeah, there is no sensors involved, no wires, no nothing, right? So it's very simple. Of course, the output is also limited, so an engine this size could produce maybe around 2 horsepower. So it's very simple, but also not performant. So during the years, this has evolved into a modern engine, which has hundreds of components. These modern engines, they have twin turbo, which means the air is forced into the cylinder by a compressor. Also, the fuel is injected into the cylinder by injector at high pressure. So we're speaking about hundreds of bars for petrol gasoline and thousands of bars for diesel engines. Also, the torque is electronically controlled. Yeah, so you have a throttle which is electronically controlled. You have injectors which are electronically controlled by an electronic control module, and then you have tens of sensors and actuators. Right, so you have pressure sensors, speed sensors, air mass flow sensors, and so on. And also actuators you have for turbo control, for EGRs, and so on. So the engine has evolved, so the power output has increased enormously, but then also the complexity, the cost, and the difficulty to manufacture has also increased, right? So that's the trade-off. Yeah, it does more things, more power. It costs more, but it has a very high power output compared to what it was hundreds of years ago. Now, why that complexity of the engine has increased? One of the reasons is because of the tailpipe emission regulations. So governments around the world starting to put in place emission regulations because they wanted to reduce the toxic gases coming out of the vehicles, especially in urban areas. So in cities where you have a lot of cars driving around, if you don't control the emissions of those cars, you can have very bad consequences on the public health because those engines will emit toxic gases. So starting from the 90s, especially in the US and Europe, the governments they started putting in place emission regulations. So in Europe, they started with the Euro standard, which started from Euro 1 around 95, and now we're speaking about going into Euro 7 from next year. And then in the US, again, we have the federal legislation, Tier 0, 1, and so on, and then we have the US California regulation, which are even more stricter than the federal ones. So again, they increased over the years. Japan kept pace with US and Europe, and then China, they started a bit later, but they currently aligned their regulation to the European and US ones. So through these regulations, the governments basically forced the OEMs and the manufacturers to improve their engines so that they emit less toxic gases. So that was better for, let's say, urban areas, but what it meant, it meant that the development cycle increased for the engine. So every time you had to design a new engine, it took longer because it was more complicated. You had to add more sensors, you had to add more software, and so on. Also, it was more expensive to design and manufacture. And then for the customer, it was a higher purchase price and also a higher total cost of ownership. So obviously, if you have an engine which has a lot of components, a lot of sensors, and so on, those components can fail. So you have to repair, and it will cost you more money. So the more components an engine has, more likely is that that component will fail. So the idea of this is that, yes, emission regulations have improved the quality of air and the health of the population in urban areas, but that meant that the price, there was a cost associated to it, and that cost was basically in the development, manufacturing, and then purchase of the vehicles. Now, what about electrification, right? So electrification, as you saw in media, literature, everywhere, there is a big push for electrification, okay? But there are some, downsides of electrification. One of them is that, for example, in the US, according to this study, a battery electric vehicle actually loses money for the OEM, right? So the profit margin for a battery electric vehicle for a US OEM is minus $4,000. That means every vehicle imposes a loss to the manufacturer instead of a profit. By comparison, an internal combustion engine, it makes a profit for the manufacturer, which is around $2,000. So this is not a general rule for all the OEMs, but the idea is that the battery electric vehicles are more expensive to produce, and then the profit margin for that vehicle is very, very low or actually negative, which means an OEM has to sell internal combustion engine vehicles in order to sustain the development and the selling of battery electric vehicles. Second, according to this study from this paper, in between 2020 and 2023, an electric vehicle has depreciated much more than an internal combustion engine vehicle, which means that if you bought, let's say, a new car, electric vehicle, after 3 years, the price of that electric vehicle was half the price you purchased. And then for the internal combustion one, the value only decreased with a third, right? So the internal combustion engine vehicles maintain their price during their lifetime, right? Which means that someone who is thinking to buy a vehicle, but is thinking to sell that vehicle, let's say in 3, 5, 7 years, they will consider the after sale price of the vehicle because it makes a big difference, right? 50% decrease depreciation is quite a lot. So there are not many people who can absorb that depreciation. And third, there is a thing called the Gartner hype cycle, right? So basically, every time there is a new technology, everybody is hyped about it, and they will going to be very optimistic in terms of how that technology is going to be, let's say, adopted by the markets. So as you can see in this plot, we have the time and we have the visibility, right? So every technology at the beginning is starting, and you have a peak and you have an inflated expectation. So everybody's saying, oh, the electric vehicles will take over and will replace all the internal combustion engines in the next 5 to 10 years, right? And as you start to develop that technology, you start to actually encounter a lot of problems, right? So problems, I don't know, with the cost, with the materials, with the manufacturing time, and so on. So as the technology becomes more mature, people realize and company realize, oh, actually, it's not going to be that fast. It's going to be slower. So you then fall from the peak of inflated expectation. You go through disillusionment, right? So at this point, you realize, oh, actually, all the estimations, prognostics were kind of false, right? But then you keep going, you keep pushing, right? And then you end up actually in the reality. You end up with a plateau of productivity. So what this means is that every time there is a new technology, everybody is very hyped about it. Everybody is very optimistic about it. And they make these crazy estimations that, this technology will become the norm in the next 5 to 10 years. And in reality, instead of 5 to 10 years, it will take maybe 15 to 20 years. So electrification went through the same process as any other, industry. So now electrification, I think it kind of reached this plateau of productivity. So it's slowly but steadily taking over market share from the internal combustion engine vehicles, but is not as fast as everybody predicted 5 or 10 years ago. To make a side point about this is what happens now with AI. So now AI is very hyped and say everybody will use AI will take all the jobs and so on. But you see, quite fast they're going to fall into reality, and then AI will take jobs slower than we predict, but it will do that, but not as fast as everybody predicts, and probably not as many jobs as everybody thinks. Right. Now, if we move into electrification, these plots basically are showing that, as I said, electrification is happening. So EVs are being sold every year, more and more. So in this plot, you have the electric vehicles sold in Europe with blue, and then United States. So what it shows is that the rate of adoption between two countries is different. So in Europe, the EVs are adopted more rapidly than the US, but the trend is the same. So as you see, the trend is growing. So 5, 10, 15, 20 years in both markets, US and Europe, EV will become dominant. And now we have China, and then the idea is that China is advancing very, very rapidly in terms of how many EVs they produce. I think they're by far the biggest producer of electric vehicles nowadays. And one of the reasons is because I think China wants to be less reliant of fossil fuels. So that's why they're pushing more for electrification. So the bottom idea is, what you have to keep in mind is electrification, yes, it will take more and more of the market share, but that takeover is going to last longer. And also, these numbers are only for passenger vehicles, right? So it doesn't take into account all the other industries which we saw in the previous slides. So what happens with the internal combustion engine? Well, the internal combustion engine doesn't just sit there and do nothing, right? So the OEMs have continuously developed the engine. So the efficiency of the internal combustion engine has increased over the years. And also it was hybridized or electrified, which means that you have your internal combustion engine and attached to it you have an electric, let's say, gearbox. So by hybridizing a powertrain, what you do is basically using the electric motor, you compensate for the disadvantages of the internal combustion engine. So Toyota, they developed the Toyota Hybrid Synergy Drive, HSD, and this power pack is basically powering the Toyota Prius and other models. But this is the first, let's say, one of the first hybrid powertrains, yeah, and it was produced by Toyota in the 90s. So what are the advantages of this powertrain? So it has higher thermal efficiency because it uses an Atkinson cycle. So Atkinson cycle is basically a cycle in which the compression stroke is smaller compared to the power stroke. I'm not going to explain, go into this detail, but the idea is that it's more efficient, even if the power output for the same cylinder capacity is less than a normal engine, is more efficient. So if you run the engine, let's say at a steady operating point, it's better to use an Atkinson cycle engine than a normal engine. Also, it has a better fuel economy, especially at light and moderate loads because of this Atkinson cycle. It has a reduced pumping loss. So basically what happens is, as the piston starts to move up to compress the air, the intake valve is still open and the air is not compressed only towards the end of the compression cycle. So by doing that, you limit your pumping losses. And then it has a lower combustion temperature, which means the nitrogen oxides are being reduced. And also it can run with a higher geometric compression because the actual compression of the air is being done later into the compression stroke. So it can run without knocking the engine, as I said, because the compression ratio is much lower due to the delay of the valve timing. So the idea is that manufacturers are improving the internal combustion engines to be more efficient, less pollutant, and also they are adding electric motors, making them hybrid, which also improve their efficiency and power output. By doing that, they make them more competitive with the pure electric powertrains, with the EVs. Right. Now you have a comparison between a Chinese BYD engine, Xiaoyun 1.5 liters. This is a hybrid engine. And this is a very high efficiency engine. Yeah. So you see the thermal efficiency of this one is around 43%, which is really, really high. Take into account that, let's say a classical atmospheric engine has an efficiency, around 30%, right? So 43% is really high for internal combustion engine. Also, it has a decent power output, 72 kilowatts, and a peak torque of 122 Newton meters. So this engine alone would not be suitable to be a prime mover of the vehicle. But if you couple this engine to, let's say, to an electric generator, and if you run it at a steady state, then you can use it efficiently in a serious hybrid, which means the engine is used to produce electricity, not to move the car. although you probably can do both. So also some other technical characteristics of the engine are a super high compression ratio, 15.5. Yeah, that's high for an engine. Usually they are around 10, 12. Again, runs Atkinson cycle. It has a cool DGR, so the exhaust gases are cooled before they are putting back into the engine. Efficient split cooling system, ultra low frictions. So the friction between the piston and the cylinder, or between the the camshaft and the valves, is very low, which improve the efficiency, overall efficiency of the engine. And then has a beltless drive system. Also on the right hand side, you see a Hyundai Kia engine. This one is a turbo gasoline direct injection engine. It's a 4-cylinder engine. It has a continuous variable valve duration. And basically the idea is that this engine has a quite good power output and torque for the displacement. So the specific power and specific torque per unit of displacement is quite high. You see, so also this engine has a low pressure EGR, advanced thermal management system, and high pressure direct injection. So 350 bars, it's quite high, right, for a direct injection petrol engine. So if you look at the parameters, compare, let's say, to an atmospheric engine, has 34% reduced friction, it has 4% increase in performance, 5% increase in fuel efficiency, and 12% decrease in emissions. So the idea is that OEMs are continuously improving the internal combustion engines, which means they are still a good candidate to be integrated into passenger cars. Right. So what are the conclusions? Why internal combustion engine vehicles are here to stay? And this means that if you want to study engineering, studying also internal combustion engines, their operations, their design, servicing and repair is still worth to be done. Because I think in the next 10 years or maybe more, there is going to be a shortage of skills, because nowadays everybody just focuses on electrification. There are not many people looking and learning about internal combustion engines. And as we saw, they are still used in a lot of industries. So as this generation of current engineers, they're going to retire, there are not many people coming and replacing them. So probably it's a good idea to go and study internal combustion engines alongside electrification, because there'll be a need for engineers, service technicians to be in the job market and perform operations with internal combustion engines. So what advantages have internal combustion engines compared to electrical powertrains? So one of them is the higher energy density, right? So energy density basically means how much energy you have per unit of volume or per unit of mass. So a liquid hydrocarbon, which can be gasoline or diesel, has around 30 to 40 more energy per kilogram than a lithium ion battery, which means that for the same weight of the power source, which can be the fuel tank, you have less mass, right? EVs compensate because they are more efficient, they have less losses, but overall, for example, for let's say trucks or maybe for cargo ships, this is a very important criteria, because you want to store as much energy as you can on board, for long trips. So going with fuel, liquid fuel, is the best option. Second is, there is a massive existing infrastructure related to fuel distribution, which are fully deployed. And then if you want to replace all this infrastructure with a electrical grid to have charging points everywhere, that's a massive investment and is very, very costly. Third is that internal combustion engines have proved their durability in extreme environments, so they can operate in extreme heat, freezing condition, high dust, and so on. Whereas for batteries, especially for very cold environments, they have reduced capacity. Also, battery has to be maintained around 20 degrees as optimal temperature, right? So imagine if you are in a very, cold country, let's say, Alaska or Siberia or so on, where you have during winter minus 30 degrees. So if you have an electric vehicle in that environment, most of the energy of the battery, or very high amount of that energy, is going to be used just to maintain and heat up the battery itself, right? So you cannot use the energy in the battery to move your vehicle. You will use that energy to heat up the battery, right? So which is very inefficient. And then another point is that, as I said, modern engines are continually to improve, so they have new technologies. These Atkinson-Miller cycle are a norm nowadays, especially for hybrid vehicles. They have high pressure injection, they have waste heat management, and so on. So they are becoming more and more efficient, less and less pollutant. So they are still a good candidate, and they can go against an electric motor. And they will be considered continuously for different markets by OEMs. Also, in terms of refueling, an internal combustion engine vehicle, to fully refuel it, it will take between 3 and 5 minutes, compared to 30 minutes to several hours for a battery recharge. This is again critical where the stand-down time for the vehicle matters. So we have commercial fleets, agriculture, and so on, where you want to just use the vehicle as much as you can doing work, not sitting and charging. There is a trend in which the electric vehicles, they can have their batteries swapped. But again, to do that requires a lot of investment and a lot of infrastructure. Because, for example, if you want to store, hundreds of batteries, if you've seen a battery of an electric vehicle, they are pretty big. So you have to have a lot of storage space for them. And also, the storage space has to meet a lot of security and safety, let's say, parameters, because electric batteries, you have to make sure they're stored properly in proper ventilated spaces, and so on. So yeah, it's quite difficult to store and maintain them. Cost is another criteria which has to be taken into account. So internal combustion engine powertrains are significantly cheaper to manufacture. They are cheaper to purchase, and also they are a bit cheaper to maintain. But okay, it's true that for electric vehicles there is no oil change. You have to service the vehicle less, because you probably only have to service the brakes and the cabin filter and so on. But for a battery electric vehicle, if something goes wrong with the battery, the cost is enormous. So if you have to change a battery, that will probably cost the same price as the car. Also, decades of manufacturing maturity. So since vehicles are being produced with internal combustion engine for a long time, over these years, it has been created a hyper-efficient, highly automated production line with supply chains, which makes the manufacturing of internal combustion engine vehicles much cheaper than the manufacturing of battery electric vehicles. And last but not least, internal combustion engines have lower dependency on critical minerals. And this is a big thing, because battery electric vehicles, they require resources like lithium, cobalt, rare earth metals for the electric motors, which makes that the supply chain is vulnerable to price volatility. Another point is that there are not a lot of areas which produce these minerals. For example, I think China produces more than half of the rare earth magnets, which makes that everybody who is producing electric vehicles and they have electric motors, they're relying on different markets to purchase those materials. So as you can see, the fight is still there. Internal combustion engines, they have a lot of applications in lots of industries, and there are a lot of complex issues. And the point is, this transition towards electrification is going to happen for sure, but it's going to happen slower than anticipated, and is not going to affect all the industries in the same way. So probably a passenger car industry is going to migrate towards fully electric vehicles first, and some of the other industries will follow. But this process is going to take years and years. It's not going to happen in the short term. And because of that, I think it's important that if you study automotive engineering, studying internal combustion engines is still something important, and you should do it if you have the opportunity. Congratulations, you have made it to the end of the video. Thank you for watching. If you like the video, don't forget to like, share it, and subscribe. And please share your thought in the comments. What do you think about what was discussed in this video? Do you agree with it? You disagree? Do you have any experience with internal combustion engines? Are you thinking, to study in university? Just let me your thoughts, and I'll be happy to reply or start a conversation. Thank you for watching. See you in the next video.